Hello all. Earlier we discussed about PMMC instrument, which is permanent magnet moving coil galvanometer. Now we will see about the true RMS responding meter. Before that, a little glance on direct current indicating instruments. Basically, this PMMC instrument is used for the measurement of direct coupled either voltage or current, and we know how exactly it works. That is, the galvanometer basically works on three general principles of operation. One is called as electromagnetic, electrostatic, and electrothermic. As you know, the Fleming's left hand rule basically works in the working of the PMMC galvanometer, and we know the torque deflection T is equal to B into A into I into N. So here, if you just see the basic equation for the torque, where T is the torque, B is the flux density, A is the area of the coil, I is the current in the coil, and N is the number of turns. And if you could just see the pointer, how it is moving on the scale, and also the hairsprings, which are basically used for the generation of restoring torque. And we have also seen the three main torques that are very much important for PMMC mechanism. One is called as deflection torque and restoring torque and damping torque. And here we have a little compensation for temperature. One is called as swamping resistor, which is made up of manganese and copper alloy. So basically we use the series and parallel combination of the swamping resistor to improve the compensation using the series and shunt resistors. And if at all you want to use this PMMC or D'Arsenal is the name of the scientist who designed this meter. So this PMMC meter, whenever we use in combination with the shunt resistor, then we could use the same thing as a DC ammeter. And the shunt resistor is equal to Im into Rm by I minus Im. This is the total current, and which is divided into two parallel paths, that is called a shunt current and meter current. So, and we did enough problems basing on this extension of ranges for ammeter and voltmeter, and also the I-turn shunt for varying ranges of ammeter. But if at all we are using this multiplier resistor or a series resistor with PMMC meter, then the same D'Arsenal moment can be used for the measurement of voltage, or simply we could say the DC voltmeter, and the voltmeter sensitivity can be given by this formula. Sensitivity is equal to inverse of the full scale deflection, ohm per volt. And if you want to use this PMMC instrument on AC signals, then you must use the rectifiers before going to apply the signal to the PMMC meter. When an AC signal is applied, the pointer of PMMC indicates as per the direction of the signal. So the average current whenever this AC signal is applied will show us a zero indication of the meter, as the pointer moves in positive and negative direction due to rise and fall of the signal. So at low frequencies it is very difficult for us to go for the uneven pointer movement, but at 60 Hz the pointer settles in average value of current in a coil, that is zero reading. So it is very much essential for us to use a full wave rectifier in order to use the PMMC for the measurement of AC voltage or current. This rectifier, as you know, converts the bidirectional signal to unidirectional, and it produces a positive deflection through the meter. And the final meter deflection, which is proportional to the average current, but actually is the RMS current, as you know. Since all these have direct relation, the scale can be calibrated to indicate the RMS value. But still, we do not recommend this PMMC to go for this RMS value or the AC measurement. We just see this true RMS responding meter. So if you could just see here, this is called as sinusoidal alternating current wave, and the right side here we have a non-sinusoidal waveforms. So this is not in the shape of sine, but it is having little spikes on it. So this is called as non-sinusoidal waveform. At a true RMS meter is widely preferable because it can measure both sine and non-sinusoidal waveforms. So here, what exactly is true RMS is nothing but root mean square is one of the three tools that can measure the alternating current. One is called as true RMS digital multimeter. The second one is RS responding digital multimeter. The third one is oscilloscopes. But the first two are usually we use for the measurement of AC signals. RMS essentially calculates the equivalent direct current DC value of the AC waveforms. More technically, it determines the effective or DC heating value of any AC wave shape. So a more sophisticated true RMS meter can accurately measure both pure waves and the complex non-sinusoidal waves. This is the block diagram of true RMS responding meter. Here you could see the measuring thermocouple and balancing thermocouple. AC input signal, which is the true RMS value, is given to this measuring thermocouple. So thermocouple is nothing but basically we use the measurement of the temperature. So whenever you apply this AC signal to the input measuring coil, then it actually gives the heating effect of the corresponding AC signal. This heating effect is given to the DC amplifier, and this DC amplifier is directly given to the indicating meter. So basically we are using this balancing thermocouple in the feedback loop in order to avoid any distortion or heating effect or for temperature compensation. Now we will see in detail about this true RMS responding voltmeter. So complex waveforms other than sinusoidal waveforms are used with this one. Here waveform heating power at thermocouple is proportional to the square of the RMS voltage. Non-linear behavior of the thermocouple can be overcome by placing the balancing thermocouple as shown in the feedback loop. So here the non-linear effect of the thermocouple can be overcome by this balancing thermocouple. So this is how the basic working of this true RMS responding meter. So whenever we apply the AC input signal, the heat at measuring thermocouple can be calculated. So the DC voltage of heat is amplified by the DC amplifier. Amplified DC is fed back to the balancing thermocouple that balances the non-linearity. Here bridge is formed by two thermocouples, and DC signal given to balancing thermocouple is equal to the AC input signal. So output indication is proportional to the input AC signal. So why do we need these two RMS meters? As you know, the purpose of these RMS meters are essential because most of the applications nowadays they are using this AC signals. For example, we see now the need for the RMS meters has gone up. We use in variable speed motor drives, electronic ballasts, or HVAC. Basically we use this computers also use, and HVAC is nothing but heating, ventilating and air conditioning, and also the solid state environments. In addition to this, true RMS meter is better choice for taking the measurements on power lines where AC characteristics are unknown. This is all about the true RMS meters. Thank you.